All right, why don't we get started? So we have an exam coming up on Tuesday in class. It'll be for the entire class period. And as I alluded to before, you're allowed one 8.5 by 11 sheet of paper, both sides, one sheet for notes that you deem as important. So the structure of the exam, as you can imagine, for a course that's based on modeling, it's rather difficult to have an exam that's a written exam versus something that you take home. And so the structure of the exam will be to test your knowledge. So there might be some definitions, some very simple hand work, certainly scenarios dealing with counting, but they won't be as nearly as complex as something that's on the homework because you're only given an hour, 15-minute class period in which to do it, and you don't have all the resources that you otherwise would have available to you when you're sitting the exam. You just have that 8.5 by 11 sheet of notes. So it'll be on Tuesday. Any questions about the exam? No questions? In terms of programming, I won't have you write MATLAB models. I might have a small snippet from an example MATLAB, and I would be asking you about the gross level behavior and some issues concerning that. I wouldn't have you implement MATLAB because it's kind of silly exercise, I think, to have you write MATLAB when you don't have MATLAB running in front of you. Okay. All right. So no questions? No questions? Okay. So that's coming up on Tuesday. All right. So where we last left off, we talked about this idea of so-called standard distributions. And stochasticity, the observation it was that for many systems, stochasticity behaves similarly. And so statisticians enterprise to come up with common mathematical definitions for certain types of structures as it pertains to stochasticity. And so the nice part about it is that rather than reinventing the wheel and starting from scratch, you can do your analyses, you can make comparisons, and more importantly, you can mechanize it, right? You can implement a program that mimics it so that you can then ask that program questions without necessarily having to go try it out with the real system. And so one example we gave was the example where choosing the gender of a team member is the same stochastically as flipping a coin. You have two outcomes, and each of those outcomes are equally likely, right? Moreover, when you make a pick, if you're picking with replacement or without replacement, doesn't matter, bless you, that the pick for one member does not influence the pick for another member. And so if we look at this idea of picking the gender for a teammate versus flipping a coin, it behaves exactly the same in terms of its stochastic or probabilistic behavior. And so we talked about the first distribution, the so-called Bernoulli distribution, and for that we said that there were two outcomes. The quote-unquote one outcome, you can call it the positive and the negative, you could call it outcome A, outcome B, it doesn't matter, it's the same thing. But we had one outcome, the one outcome, and that occurs with some probability P. And so as a proper probability, P is between 0 and 1, inclusive of the endpoints on the real number line. And then the probability, by law of total probability, for the other outcome, the 0 outcome, is just 1 minus P. And so we computed the expectation and we did that out. I won't repeat that here. And we also computed the expression for the variance. And so if you're given a scenario or a problem and you want to model it, and it is a stochastic system, and it exhibits this quality where you have a two-way outcome, one of which occurs with some probability, you can absolutely model it as a Bernoulli distribution. Okay. We also talked about the binomial distribution. And for the binomial distribution, it was related to the Bernoulli, and the binomial consists of a number of trials and many trials. And each one of those trials has a certain structure in that each of those single and many trials can have two different outcomes. So suppose, if you were like in a kindergarten class or whatever, and you were going to decide, let's have ice cream, and you ask them, do you like chocolate or vanilla, right? You're going to have n students, maybe n is 20 kids in the class, and then you're going to ask each one. That is a two-way choice for each of these n many choices, and you're going to ask each one the outcome, is it chocolate or vanilla? So if you wanted to talk about the expectation, right, because the expectation might be something you use to determine how much ice cream you would have to buy ahead of time, certainly you can model this as a binomial distribution. So for the binomial, we have some number of trials, and each of those trials is associated with a two-way outcome, either the +1 outcome or the 0 outcome. And what you're looking for with this Bernoulli, or binomial distribution rather, is the probability of having a certain number of so-called successes. In the case of the standard that we're using in this description, a success corresponds to a 1 outcome. Now, you could have a success correspond to a 0 outcome if you choose. The math works out exactly the same. And so what you're looking for or measuring for the binomial distribution is the probability that you're going to get a certain number of successes, x many successes. And so the probability functionally looks like n choose x, where n is the number of trials, x is the number of successes, p, the probability of success raised to the x power, times q, which is 1 minus p, exponentiated to the n minus x power. And so we left it up to you I left it up to you, we needed a book also, to work out the expectation and the variance on your own for it. I think we did the expectation. Okay, any questions about this? So that's where we left off. Okay, so let's continue on with yet another distribution. And this is called the geometric distribution. The geometric distribution derives its name from the geometric series, and we'll talk about that along the way. So suppose you have a sequence of 2 outcome observations. Now, we said the binomial distribution was a sequence of 2 observations. Well, so is the geometric distribution. But the geometric distribution deals with a specific scheme as it pertains to that sequence of 2 outcome observations. So let's frame this with an example. Suppose you're a business owner. And as a business owner, you're enjoying some success and you want to expand your business and you have an open job requisition. You're going to hire someone. And you have a bunch of candidates that are waiting to be interviewed for this job. And of course, you're going to go ahead, you're going to talk to them. And let's assume, for the sake of argument, that you have no preference for any one candidate. It's just when the quote-unquote suitable candidate or the right candidate comes along, you're going to end up hiring that person. Okay, so let's take this scenario and carry that forward. So let me ask you, how many people do you interview before someone is hired? That might be a question you want to ask because these interviews aren't free. Now let's ignore the fact that budgets are real and you can't spend an infinite amount of money to fly people out, to interview them, and so forth. Moreover, you're also spending money when you have somebody call that person for phone or Skype or video conferencing style interview because you're paying the salary of the person who's spending time into conducting the interview. So let's set aside the idea of cost. So let me ask you, do you know how many people you're going to interview ahead of time? Do you know? No? 5 people? 10 people? You don't know, right? Neither do I. It's not a trick question. So this idea of the number of people you're going to interview before someone is hired, that's an important thing that you might want to know. You don't have control over the number of people, right? And you also don't have control over whether or not the first candidate, the second candidate, third candidate, and so forth is suitable, and that's ultimately going to be the person that's hired. So it is absolutely stochastic. So if it's stochastic, how do you know how many you're going to interview? Don't know. So we need a framework for talking about that. So let's do that. Let's talk about that. So let me first ask you this question. When I mentioned how many people do you interview before someone is hired, were there any restrictions on how many interviews you are able to afford or you can conduct? Did we set a restriction on that? No, we didn't. So if we didn't set a restriction, and this is a really important point, anytime you have a scenario, do not inject your own constraints on the problem. Only inject constraints that are specified in the statement for the problem, okay? So no, we didn't have any restrictions on the number of interviews you could conduct. Now, certainly, you know, companies have limits. You have budgets. You're not going to spend, millions of dollars trying to hire one person. Maybe in some cases you might, depending on the job at hand. But it's not typical to do that. So, did the description say you had a preference for any particular candidate? Right? You weren't doing any filtering. Now, certainly when you advertise, only people who believe that they're suitable or interested in the job would apply. But that aside, you didn't have any preference. So the answer to that question is no. You're only placing restrictions on the problem that are stated by the problem definition. So just say no. Do not introduce things into the problem. Do not introduce any information beyond what is stated in the question or the scenario. And so fast forward, kind of going towards the 2/3 point in the semester and towards the end of the semester, what I'd love for you to be able to walk away with, and you will, is to take a scenario, a description, right, some sentences in English, and be able to model this probabilistically. So it's going to be really important from now going forward to make sure you're not injecting or adding things to the problem that aren't stated in the problem definition, right? Those are called free variables, things that you do not have restrictions for. Do not set restrictions that are not part of the problem. Okay, so let me ask you, how many people is it possible to interview if I don't have restrictions? Anyone venture to guess? How many? As many people as you want. Good. So theoretically, the whole population on Earth, right? But we didn't set the restriction to population on Earth. I know it sounds kind of silly, but any number that we want. So how many choices, I ask you another question, how many choices are there if you're going to either hire or not hire a particular candidate? Now, it might seem obvious. You have two choices. You either hire them or you don't hire them. There's no hire maybe, right? Either hire or don't hire. Okay. So let me ask you another question. It's not a trick question. At what point do you stop interviewing candidates? In the simple case. When do you stop interviewing? When you find one. Okay, great. When you find one. Absolutely. So since there's no restriction on the number of interviews, assume that there are a countably infinite number of people in the pool of candidates. There can be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... Right? For each candidate, you can either hire, that's one alternative, or not hire. So you have two choices. Okay? And of course, you stop interviewing when you hire someone, because the whole purpose is to find a candidate to fill the job. Okay. So now we're not talking about, you hire one and you have a backup just in case the first person turns down the offer. We're not talking about any of that. That was not stated in the problem. Okay. So we have these three characteristics from this scenario, right? Okay. So we know it's stochastic, and we want to be able to talk about this idea about the likelihood that some particular person in that number of candidates is going to be the one you're going to hire. Okay. So let's model this mathematically. So we have these candidates, and we can order these candidates. It doesn't matter how they're ordered. They could be in terms of their alphabetical order, or by the name, or it could be in terms of the order in which they submitted their resumes. It doesn't matter, but you can find some ordering. So in this ordering, you have the first candidate, candidate 1, and then after candidate 1 is candidate 2, candidate 3, 4, 5, 6, 7, 8, up to some nth candidate. Now, n does not have a definition. It's just a variable, and it's going to be a natural number. And so n is without bound, right? So that's one way of describing this idea of without bound. N can be anything, but we do know it's a natural number. Okay. Does that make sense so far? Any questions? All right. So let's start with a base level analysis. And for candidate 1, there are two choices, hire or not hire. For candidate 2, there are two choices, hire or not hire. And for each of those n many candidates, there's a choice either to hire or not hire. So one thing that you could do, say, gosh, how many different ways can I hire or not hire? Well, you could think there are 2 to the n possible choices of success or failure, i.e. higher or not higher, or heads and tails if you want to call it that. But if you did that, that would be incorrect. And the reason why it's incorrect we'll get to in a few moments. But let me ask you, and it has to do with what we just got done talking about, is there something we're forgetting in this analysis when we say 2 to the n choices of higher or not higher? Is there something we're forgetting?
Is that including everybody?
For everybody that you could interview, all n people, and n is a number.
Once you hire someone, it doesn't matter about everyone.
It doesn't matter about everyone else. Okay, good. So it's not just any arrangement of higher, no higher decisions. We are going to limit our arrangements to arrangements that have specific structures. Okay? All right. So yes, there is something that we're forgetting, and it's not correct because we consider all possible arrangements. We're forgetting a bunch of things, and I'll kind of talk about what those things are, but as was just said, once you hire someone, you're not going to consider the rest, right? So that means these slots are going to have particular values, not just any possible combinations of higher, no higher outcomes. Okay. So let's introduce a kth candidate. And this kth candidate is going to sit somewhere between the first candidate and the nth candidate. Now k could be exactly 1, or k could be exactly n. If k is exactly n, it's the last candidate. If k is exactly 1, it's the first candidate. And this kth candidate, that's going to be that person where you encounter them, you interview, and you say, yes, let's hire this person, right? So let's designate this kth person as being the one that you say, yes, I'm going to hire this kth person. So here we have candidate 1, candidate 2, and somewhere in there is candidate k, followed by candidate up through candidate n. Okay? Does that notation make sense? And so I'm putting kth candidate between the first and the nth. I don't know where exactly it is, so I just choose a spot. And k could be the first one. You could get lucky. The very first person you interviewed is the one you hire. Or you could be unlucky, right? Some notional last person where n can be infinite, countably infinite, is the one you end up hiring. Okay? So this kth candidate, let's designate him or her as the one that you actually hire. That outcome is a positive one. Okay. So k is somewhere after the first candidate and somewhere before the nth candidate, and k could absolutely be exactly the first or exactly the nth. It doesn't matter where k is, but k is a distinct one that we can identify as the one that you hire. Okay, so if the kth candidate is the one that you hire, is there some property associated with all the people you interview before the kth person? Is there some property? If you hire the first, what had to happen for everyone before the kth? I'm sorry, if you hire the kth, what property is associated with people before the kth? They weren't hired. Okay, good. So that means everyone before the kth wasn't hired, because if somebody before the kth was hired, then k wouldn't be the one that was hired. That's what we specify. Somebody has to be hired, right? Okay, so that means we need a way, mathematically, to express this idea of before the kth in terms of position. Okay, so how would we express somebody's order if they're before the kth? How would you do that? Any guesses? What's your intuition? If I'm number k, the person right before me is number what? K minus 1. So that means we have the first candidate, the second candidate, the third, fourth, up to and including the k minus 1th candidate. All of those candidates were not hired, because by definition we're designating this kth as the one that was hired. Okay? Okay, good. So what about everyone interviewed after the kth? Is there a property associated with them? Were they hired? Do you care? No. You only care once you hire somebody. So we mathematically need a way to describe this idea of after the kth. So how would we describe right after the kth position? K plus 1. K plus first position. So That would mean the k plus 1th, the k plus 2nd, the k plus 3rd, up to and including the nth, are after the kth person in line. Okay. So now we've developed a little bit of machinery that we're going to use mathematically to identify the sequence of people. And now we can describe properties associated with that sequence because we're not going to use all possible sequences of success and higher outcomes. We're only going to use certain sequences of success and higher based on the definition of this problem. Okay. Any questions about this? Does that make sense? Yes? No? Okay. So we have a failure outcome for the first through k minus 1th candidates. Because for each of them, if the kth is the one you hired, there would be a not hired, not hired, not hired, not hired for each of those first through k minus 1th candidates in line. Then you have success. You're hired for the kth candidate. And then for everyone after the kth candidate, the k plus 1th on through the nth, we don't really care about them. You hired, so you don't even consider them. It doesn't matter. So now we're limiting our structure, our set of outcomes, to be a sequence of failures that end in a success. And that particular sequence in any system for which each one of those decisions is a two-way outcome, where you have a sequence of failures ending in a success, that is governed by a geometric distribution. Okay? Any questions about this? Does that make sense? Okay. So we'll take a look now. Well, I think I answered that. It's a geometric distribution. Each interview has a two-way outcome. And because it has a two-way outcome, and there's a probability associated with the success versus the failure outcome, you can model each one of those individual decisions as a Bernoulli random variable. Okay? And so we have the geometric distribution is a special case of a sequence of Bernoullis that has a particular form. All failures ending in a success. Okay. So you have a sequence of so-called Bernoulli trials. Interview the first candidate, like flipping a coin. Interview the second candidate, like flipping a coin. Interview the third candidate, like flipping a coin. And then once you get that case thing, that's where your success occurs, you stop. And so what someone might want to know is, what is the probability that I'm going to end up hiring the 5th candidate, or the 7th candidate, or the 12th candidate that interviews? That's something that you might want to know. So this number k, it's an outcome, it's a function that's computed over an observation sequence, and your observation sequence says failure, 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 success. And what it's outputting is the position, or the count, or the order in line when you have this single success. So this k position is absolutely the outcome of a random variable. Okay, it is a random variable that governs it. Any questions about this? No? No? Okay. So the goal now is to try to determine what is the probability that you hire the kth person. Because one thing you might want to know, what is the probabilistic average, the expectation that you're going to hire someone, and that's the average person in terms of their number, the average number of times you're going to have to interview in order to get the candidate, and that's going to impact your dollar cost at in the end of it all. So, what is the probability that you hire the kth person? And that's what we're going to develop, and this is called the geometric distribution. So, for Bernoulli random variable, since each one of these interviews for each candidate, each position for candidates in line to be interviewed, is a Bernoulli random variable. So one of the questions you want to know is, what is the rate of success, right? What is the probability of a higher decision? Well, probability of success we're going to call P. Now P could be 0, P could be 1, P could be somewhere in between on the real number line. And the rate of failure, by law of total probability, is just 1 minus P. And so oftentimes in the literature, you'll see people abbreviate 1 minus P as variable Q. So we have P is the probability of success, you're hired, and Q is the probability of failure, you're not hired. Okay? All right. Any questions about this? Make sense? Okay. So let's mind our P's and Q's. And we have all of our candidates, candidate 1, candidate 2, candidate 3, and so forth. Candidate K somewhere in the middle. And then we have candidate N all the way on the end. Now, of course, if you have a candidate K, the person right before candidate K is going to be candidate K minus 1. So let's do this. Let's annotate each candidate with the probability of either success or failure. And we just got done saying that this particular sequence of successes and failures are going to have all failures, and then it's going to end in a success, where that success is at candidate K's position. So let's do that. So candidate 1, we have a failure. Candidate 2, we have a failure. Candidate 3, we have a failure, etc., up to and including candidate K minus 1. And then we have that single success, you're hired, associated with candidate K. So now we're going to substitute for each of these outcomes. We're going to substitute the probability for which those occur. So below candidate 1's failure, we're going to write 1 minus P. Below candidate 2's failure, that's a probability of 1 minus P. Likewise, up to and including candidate K minus 1, we're going to write 1 minus P for the probability of each of those failures. Okay. So then we have candidate K, which was success, you're hired, and we're going to write that probability, which we just said was P. Right? Each one of these is a Bernoulli random variable. Okay? But unlike the binomial distribution, with the geometric, you have to have all failures and you end in a success. So binomial, you can have your successes and failures interleaved all throughout the string or sequence. Okay? Any questions about this? That make sense? Okay. So now, each one of these failures, right, they're independent. One failure does not impact the other failure. Each candidate is considered on the merits of his or her resume and qualifications and interview and suitability assessment for the job. Okay, so because they're independent, we're going to compute the probability of this entire sequence from candidate 1 up to and including candidate K by multiplying the individual probabilities for each one of these Bernoulli trials. So let's do that. So we have P for the success times 1 minus P times 1 minus P times 1 minus P times 1 minus P. And this one time P is probability of success. That's for candidate K's probability. And then this 1 minus P, how many times do we multiply 1 minus P by itself? Let me ask you. How many failures do we have? We have K minus 1 failure. So we're multiplying this probability of failure, 1 minus P, quantity, by itself, K minus 1 many times. And of course, when you multiply something by itself some number of times, that's the same as exponentiation. So we multiply this 1 minus P, K minus 1 many times. So we have 1 minus P equivalently raised or exponentiated to the K minus 1 power. So now our expression is P times 1 minus P exponentiated to the K minus 1. And again, we can summarize this 1 minus P with variable Q. So let's do that. And we get P times Q to the K minus 1 power. Okay. Does that make sense? Any questions about this? So we're translating from the schematic that talks about the candidates to some math that describes the probability of this particular sequence, K positions long, where the first K minus 1 positions are failures, and the Kth position is a success, where each interview is governed by a Bernoulli random variable. Okay. So now, let's treat then this probability as a P times Q to the K minus 1, or P times 1 minus P to the K minus 1 power. Those are two equivalent expressions. So the probability, P of x, is the probability that the first success occurs on the trial number x, right? And that's equal to the number of failures, so that's 1 minus P to the x minus 1 power, because the first x minus 1 are failures, followed by that singular success at the end, at position x, which is P. So now we're going to use this expression as our probability. And of course, our x can be unbounded because we're not placing any restriction on how many people you can interview. Let me do a time check. Okay, so because x is unbounded, x could be 1, 2, 3, it could be infinite. It's countably infinite. That was unbounded. We didn't set any restrictions on it. And of course, because these are candidates, we can't have fractional values, right? We can't have rational numbers or real numbers because there's no such thing as person number 1.3. That just doesn't fit the scenario. Okay. So you notice that we had this 1 minus p exponentiated times p, and we didn't anywhere have this n choose k, right? N choose k, that's a binomial thing. That's not a geometric distribution thing. And the reason for that, and I stress this, is that the geometric distribution talks about specific sequences where you have all failures and you end in that singular success. Okay, so the failures must precede the single success to be a geometric distribution. You stop once you find someone who's suitable. Okay. Any questions about this? Okay. So now, seems like a little bit of trickery, right? How can you say unbounded, right? You need to actually compute a value, right, the probability of, but then this x you're saying is unbounded. I've never heard of something that's unbounded when we talk about probabilities, because you want the probability that the 10th person is higher. You don't say that the infinite person is higher. It doesn't make any sense. This is really a probability. Well, we can actually prove this. And like we said, to be a probability, one of the properties that you have to have, an important one, is this law of total probability. What that says is if you add up all the probabilities for all the possible outcomes you could have, that adds up to 1, right? So, okay, well, if we say the probability of x, for all those x's, we sum them together, that summation should total 1. So the left-hand side of equality here, that should equal 1. So let's actually prove that. Now, of course, we just got done saying that x is unbounded. It's uncountable, it's countably infinite. So our x is going to start at 1 because you don't start at person 0, you start at person 1. There's a first person in line waiting to be interviewed. So this summation, the bottom index on the summation is x is going to equal 1, and then on the top it's going to be infinity. So x is going to be 1, 2, 3, 4, 5, and so forth, up to including infinity. And the probability, we said, was this 1 minus p to the x minus 1 power times p, right? So that's our probability. So we're literally here in this second line, we're substituting our expression for the probability, where p of x is, and we're going to show that this infinite summation is going to equal 1. Do you believe me? No, you shouldn't, because you should say, let's prove it. Okay. So let's do so. So in order to do this, we're going to take a brief detour, and we're going to talk about the geometric series and geometric sequences, right? Because we're going to need this machinery in order to go from this expression that we have for law of total probability to actually prove it, because we have this infinite sum. Okay, make sense? Any questions? All right. Have people done sequences in series? No? 1, 2, okay. All right. So a sequence, a geometric sequence, is called geometric sequence because there's a relationship between each term in the summation and the next term. So of course we start at the left here, and this is an example of a geometric sequence. 1 plus 1/2 plus 1/4 plus 1/8. And not only do you just have a sum of terms, that relationship to be a geometric sequence is that each successive term, your neighbor to the right, has a value of your value times some constant, right? And in this particular case, that constant is 1/2. So here we have 1. If we multiply 1 times 1/2, we get 1/2. Here we have 1/2, our second term in this sequence, or this sum of terms. If we multiply 1/2 by 1/2, we get 1/4. If we multiply 1/4 by 1/2, we get 1/8, and 1/16, and so forth. And this sum can be infinite. It can also be finite. And as you can imagine, if you are a geometric sequence and the term is something that's less than 1, it's a fraction. If you multiply a fraction by something enough times, if you multiply a fraction enough times or apply that multiplication enough times, eventually it goes to 0 because it keeps getting smaller and smaller and smaller and smaller and smaller. Okay. So this is an example of a geometric sequence, and the constant factor defining the subsequent or successive term in this geometric sequence has to be a constant factor. That's what makes it a geometric sequence. So more generally, if instead of saying 1, 1/2, 1/4, 1/8, we can talk about a generic quantity, we call that R, right? And so if you have in the first position R to the 0 power, that's 1, and if you multiply that R to the 0 power by R, you get the second term, that's R, and if you multiply that by that constant R, you get R squared, R cubed, and so forth. So that's also a geometric series, but now we've just replaced 1/2 with some value R, where R can be any value, okay? All right, any questions about this notation? Does that make sense? Okay. So this is what a geometric series is. And this leading term is really just that constant raised to the 0 power, because anything raised to the 0 power is a 1. Okay. So in addition to raising each successive term by multiplying each successive term, in addition to computing each successive term by multiplying the current term by that constant R, we can also multiply the whole thing by a scalar. And the reason why that works is that if you have a sequence, right, under a summation, 1 plus R squared plus ... Well, that's a summation. You can put a parenthesis around that, so do that summation first, and you can multiply the whole thing by a constant A, and the distributive law of multiplication over addition takes hold. And so you can multiply this A by the first term, multiply the A to the second term, multiply the A to the third term, and so forth, even if it's an infinite sequence, right? And so the general form says, not only do I have each term, the next term, computed by multiplying by that constant R, I also can take the whole thing and multiply it by another constant A and take advantage of the distributive law. Okay? So in full treatment, I have A, which is really just A times R to the 0 power. If I multiply A times R to the 0 power by R, that's just A times 1 times R, and then I have A times R times R, which is R squared, and so forth. So that is the full treatment for a geometric series. Any questions about this? Make sense? Okay. So now we're going to do a little bit of interesting manipulation. We're going to take this full treatment for a geometric series. So we have A plus AR plus AR squared plus AR cubed plus AR to the 4th and so forth. And we're going to collapse this notation using a summation symbol. Now we said this is an infinite series, and so it goes on without bound, but we're going to write it more compactly. So how we write that, we have our summation, and the summation index variable is k, and then each term is a times r to the k power. So let's think about what this means, right? If k is equal to 0, right, we get a times r to the 0 power, that's just a times 1, or a. If k is equal to 1, we get a times r to the 1, well, that's just ar. If k is equal to 2, we get a times r squared, right? So absolutely, this is a compact representation of this infinite series. And then eventually we're going to get a term that's going to be a times r to the infinite power, okay? Because it is an infinite sequence. So there's a result, and we'll actually prove this result, that this infinite sequence in its full form, it has a closed form expression. And when I say closed form expression, I mean an expression that ends, right? It doesn't just have ... and goes on. This infinite sequence, this sum, for k goes from 0 to infinity of ar to the k power, is equal to A times quantity 1 minus r to the n upon 1 minus r, right? So we're going to actually prove that. Okay. So how are we going to do this? Well, let's first write out what we're going to call S. S is going to be the sum of all the terms, which is our geometric sequence. And so we're going to start out with the A term, AR squared, AR cubed, plus up to and equal to the addition of AR to the n minus 1. Okay. So if we do that, we can multiply both sides of that expression by r, right? If you multiply both sides of equality by the same term, the expression does not change. So S is where we're going to call the result of that geometric series, right, the sum, and we're going to multiply left and right by this term r, right? And r just happens to be the same constant that defines the geometric series. So if I multiply r times s, I get rs on the left-hand side of equality. If I multiply the first term, a, which is also a times r to the 0 power, I get ar. ar, if I multiply by r, becomes ar squared, and then I get ar cubed, ar fourth. And that last term, ar to the n minus 1, becomes ar to the n minus 1 times r, which is the same as a times r to the n power. So that's just multiplying both left and right hand side of this sum, representing S, representing the sum of the geometric series, multiplying left and right side of equality by that same constant r. All right, does that make sense? Any questions about this? So then, why did I do this? Well, it's not my original proof, it is a proof about the closed form expression for the geometric series. It's done because the geometric series is infinite, and if it's infinite, it's hard to deal with. And so what they do is set a variable n, and then you take a limit as n goes to infinity to show that this works for the infinite version. Okay, so we take our sum, right, for a total of n terms, the term that has r to the 0 up through the term that has r to the n minus 1, that's n terms. And then we multiply both sides of equality by that constant r. So now, this is a bit of a mess, and we want to get rid of some of these to try to reduce it down to this expression that we have up above, a times 1 minus r to the n upon 1 minus r. So what we're going to do now is we're going to subtract. We have two systems of equations. We have something equals something, right? That's my first equation. Here's my second equation, rs equals something. It's kind of the same equation, only the second equation is just a version of the first equation where we've multiplied both sides of equality by a constant r, right? And it's the same r that occurs in the geometric sequence. So what we're going to do is we're going to subtract one of these equations from the other, right? So I'm going to do the subtraction where I'm going to take the bottom equation, rs equals blah, 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 and I'm going to subtract that from the top equation. So I'm going to write a big minus sign out here, and like you're doing, arithmetic. And we're going to notice something. If I say minus, well, this minus should be further out there because I don't want it to look like I'm negating rs, right? And what I mean by this minus is similarly for, when you're doing arithmetic, you might have 49 minus 11. I'm doing that similarly, but I'm using whole equations instead of just values. So if I subtract the bottom equation from the top equation, well, let's first look at the left-hand side of equality. If I, question?
Oh, no.
Okay, I should just erase that thing because it kind of is sticking out there. Let me see if this works. Do that. Oh, yeah, that's part of the slide. Okay, all right. That's right. There we go. Let's let me back in. There we go. So if I accidentally advanced the slide. All right. So if I subtract, let's first look at the left-hand side of equality. If I subtract rs from s, that's s minus rs on the left-hand side of equality. Okay. So now we're going to look at the right-hand side of equality. I have terms here that begins with a for the top line, a plus ar squared, etc. And on the bottom term, I have ar, the bottom equation, ar plus ar squared plus ar cubed, and so forth. So if I kind of observe the pattern, I see that I have an AR up top matched with an AR down bottom. I have an AR squared up top matched with an AR squared down bottom. Likewise, AR cubed, and there's an AR to the 4. And I have an AR matched with an AR n minus 1 and a to the r n minus 1. So if I match them up, I make an observation that I have similar terms for most of them, if not all of them, on the right-hand side of equality for the top equation as well as the bottom equation. But what's left over? Well, what's left over, I have this a term in the top equation, and then I have this a times r to the n in the bottom equation. So if I'm subtracting, well, similar terms, you subtract something from itself, it goes to 0. So this term, that subtraction goes to 0, that subtraction goes to 0, that subtraction also goes to 0, and also this subtraction, a times r to the n minus 1, that also goes to 0. What's left over is I have a positive a, right, that's up top, and I'm subtracting the bottom equation, so that's a minus a times r to the n. So on the right-hand side of equality, after I do that subtraction, subtracting the second equation from the first one, I have a minus a times r to the n power. Okay. Does that make sense? Any questions about this? Yes? No? All right. So now that I have this expression, I'm going to do a little bit of factoring. On the left-hand side of equality, I can factor out a common s, and on the right-hand side of equality, I can factor out a common a. So let's do that. I have s times 1 minus r. On the left-hand side, I have a times quantity 1 minus r to the n. So now, okay, all I do is I divide both sides of this expression by 1 minus r, and that gives me exactly s times a, s equals a, rather, times 1 minus r to the n upon 1 minus r, which is exactly what I was trying to prove up above. Okay? Any questions about this? Does that make sense? So why did I do this? Well, I did this because I want to be able to use this geometric series to show the law of total probability for my geometric distribution. But I had this confounding issue where this x, the position of the person that I hired, is unbounded. It could be 1, 2, 3, 4, it's countably infinite. And it's really hard to perform any operations with a large sequence. And so I'm trying to find an equivalent mathematical expression that describes what the result is of doing that sum, right? And that's called a closed form solution, okay? So there's my closed form solution. Let's take a look at this next point. And so this assumes that r is not equal to 1, right? And the reason why they do that is because if r is equal to 1, well, of course, this becomes infinite, right? It doesn't work. It falls apart. So because it falls apart when r is equal to 1, when r is equal to 1, the denominator becomes 0. They just say, all right, forget about r equals to 1. Let's forget about that case. It was one of those fix-ups that we talked about before. That happen all over mathematics. Okay, so r is not equal to 1. So let's take a look at this other case. If r is less than 1, right? Well, probabilities, for the most part, are less than 1. So this could work for a probability, right? And remember, these P's and Q's we talked about for probability of success or failure in terms of the hiring decision, we said those were Bernoulli random variables. And so as Bernoulli random variables, it's either P or Q is the probability. So yeah, that kind of fits for this case of being less than 1. So for r less than 1, this expression, a times 1 minus r to the n over 1 minus r is equal to a times 1 over 1 minus r. And the reason for that is that if our sum is infinite, this exponent n is infinite. And if this exponent n is infinite and r is less than 1, if you multiply something that's less than 1, some decimal point, by itself enough times, eventually it goes to 0. And let's demonstrate that. So you'll note here also another pattern. here we have our sum, and that sum, the top bound of this, the index of this summation is n minus 1, but the exponent is n. So anytime you write this identity, the exponent here, r to the n, is always one more than the upper index, the bound on that summation. Okay? So that's just a pattern that we'll just observe and remember. Okay. So if we have a times r to the k power in a sum, right, where it sums n plus 1 terms, where k goes from 0 to n, we use the same pattern, a times 1 minus r to the n, one more than the summation index, summation bound, so that's r to the n plus 1 over 1 minus r. We're just plugging in using our pattern. Okay. So let's take a look at this. So suppose our a is equal to 1. If a is equal to 1, our infinite series is 1 times r, that's r squared, r cubed, and so forth. And how we can solve for this in closed form is we have our terms, 1 times plus r squared, and so forth, up to including r to the n power, and we take the limit as n goes to infinity, right? So let's try that out. And so here, this represents the following expression. So this is a times r to the k, a is equal to 1, right? We have our r to the k, and that's equal to 1 minus r to the n plus 1, so that exponent for the r here is 1 more than the upper bound on the summation, over 1 minus r. So if we do this, we're basically taking the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. Now, of course, we stated that r is less than 1. So if r is less than 1, and you exponentiate something that's less than 1 enough times, an infinite number of times, it goes to 0. If you don't believe me, try it yourself. If you have 0.1 times 0.1, that's 0.01. If you multiply again times 0.1, that's 0.001. Multiply again by 0.1, it's 0.0001. And so if you do that an infinite number of times, it goes to 0, right? So that means this term here is going to go to 0 because r is less than 1. The magnitude of r is less than 1. Okay? Does that make sense? Any questions about this? Okay. So we do that, and we get this final result. For r less than 1, this infinite series is equal to 1 over 1 minus r. So why did we do this? We're going to use this identity for the probability and compute the total probability, but that total probability for the geometric distribution, because x is unbounded, we get an infinite series. And this infinite series is the geometric series. And we're going to use this identity, 1 over 1 minus r, to substitute a closed form expression so we can actually prove the law of total probability that the geometric distribution is in fact a probability. Okay. Any questions about this? Okay. Let me do a time check. 54. Okay. So let's continue on. Probabilities absolutely satisfy this property. Probabilities are, for the most part, less than 1. Right? The max a probability can be is exactly 1. So this is going to fit very nicely with a probability. Okay, so let's go back. First, any questions before we head back? We go back? No? Okay. So we left off here, and we had this probability that we developed, and this probability said the first x minus 1 candidates have a failure. And so we multiply 1 minus p by itself, x minus 1 many times, right? And then we have that xth person in line was hired, so that's a success. And that had a probability p associated with it for the Bernoulli random variable. And so we wanted to show that this is actually a probability, this 1 minus p to the x minus 1 power times p. And so if it is a probability, then if we sum together all of the probabilities for all possible outcomes, that should sum to 1. And so this is our law of total probability. It says if you add together for each value of x, the probability of x, the sum of all such x's is going to be equal to 1. So we substitute this expression for our probability for the first success occurring in the x position in line for that person. This is our expression. We're literally substituting the probability expression we had above. So we have an infinite sum. X goes from 1 to infinity of 1 minus p to the x minus 1 power times p. And so what we want to demonstrate is that expression, that summation of all those terms is equal to 1. And we'll treat this, and we notice that this is exactly a geometric series. So before, let's go back and look at our geometric series. We said the geometric series has a form a times r to the k power, and we're summing an infinite series from 0 to infinity. Well, here, we're not summing from 0 to infinity, but we're summing from 1 to infinity, right? And we have something times something. So if we treat p as our a term, now p is a probability, it's a constant. A is a constant. So we treat p as our a term, and we treat 1 minus p as our r term. So if we do that, well, what do we get? We have the sum where x goes from 1 to infinity, and we said p is our a term, so we and 1 minus p is our r term, so we have r to the x minus 1 power times a, right? So this is just a straight substitution. We call this r, and we call the p, we call that a. So that's exactly, if we just rearrange the terms, because multiplication is commutative, you can reverse the terms and it's the same. A times r to the x minus 1 power. That's exactly the form of a geometric series. And as a geometric series, well, we know that we can't have this infinity as the upper bound on the index for our summation. So what we're going to do is we're going to change this to be x goes from 1 to n, a r to the x minus 1, and just set a limit as n goes to infinity, okay? And that's the same as doing it as an infinite sum. Does that make sense? Any questions about this? Okay. And so because it's a geometric sequence, I'm just going to substitute the result that I had from before. And the interesting part is, you say, gosh, well, in your sequence, didn't it start from 0, right? Yes, it did start from 0. K goes from 0 to n minus 1 of ar to the k power. But this one starts from 1. If you have x equals to 0, right? Let me see where I left off. Oh, brain fart. Yeah. Okay, all right. So one thing you can do is a so-called change of variable on your index, right? And so the problem is here, when we have the definition of our geometric sequence, you'll notice that it always starts at 0, right, and goes to infinity. But here, we start at 1 and go to infinity. So it's not quite a geometric sequence because we have a missing term for x equals 0. So one thing you can do, you can actually just change your variable, right? So let's say let k let k equal x minus 1, right? So now if you let k equals x minus 1, you have k equals 1, right? Because x is 1 here. And you could call that infinity minus 1, but infinity minus 1 is just infinity, right? So we can write infinity here. Okay. So we do that, and we have 1 minus p to the k power, and then we have p here, right? So you can change the bounds on the index for the summation by just changing variables and with a switch, and this is the equivalent expression. And because infinity minus 1 is also infinity, we just write the infinity there, okay? All right, so now that fits, I'm sorry, no, did I do that? K equals 0, x minus 1, I did that wrong. X is equal to k plus 1, k equals x minus 1, no, that's right. So that should be k equals 0. That's right, k equals 0. All right, made a typo there. All right, so k equals 0. So this is a proper geometric series. So as a proper geometric series now, we can change this upper bound here to be n, and then take the limit as n goes to infinity. Okay, so what we do is we rewrite that to be k goes from 0 to n, 1 minus p to the k power times p, and we take the limit as n goes to infinity. All right. So this form, where I change the summation variable to k, it fits exactly what we were talking about for this geometric sequence. The geometric sequence said we can use this substitution if our summation goes from 0 to infinity, which it exactly does on this next slide. Okay. Any questions about that? Does that make sense? Yes? No? All right. So let's go forward. So we make that substitution, and we take our limit, and with that substitution for n, remember we said when we do that substitution that if we had an n up here, the exponent is always one more than the upper bound of that summation. So what we're left with, again, we said 1a times 1 minus r to the n plus 1 power over 1 minus r, right? That was the result of our geometric sequence. So in this case, a is equal to p, and r is equal to 1 minus p. So we're just going to make that substitution where a is equal to p. So everywhere we see a p, we're going to write an a, we're going to write p. Everywhere we see an r for this result for the geometric series, we're going to write a 1 minus p. And so we do that, and this is our expression. So it's 1 minus r, right, 1 minus p to the n plus 1 in the numerator. And then in the denominator, we have 1 minus r. Well, for r, we substitute 1 minus p. Okay. And then we multiply by a, where we're substituting p for a, and we get times p. So if we do that, well, what do we have? And of course, we're going to take a limit as n goes to infinity. So if we look at the denominator, we'll first draw our attention to the denominator. We have 1 minus 1 plus p in the denominator, if we carry out that subtraction, which is just the same. Well, that goes to 0, and we just have p in the denominator. And then we have a 1 minus quantity 1 minus p to the n plus 1 power in the numerator. Okay, so, and we have a p here. So in the denominator, we had 1 minus 1, so we had a p left in the denominator, so that leaves p in the denominator, and we're multiplying by p. So the p in the denominator and the p there cancels, it goes to 1, and we're left with 1 minus p to the n plus 1 power. Okay. Does that make sense? Any questions about this? Okay. So that's what we're left with. And so now we take the limit as n goes to infinity. Now, as n goes to infinity, if we take that limit, so it's really the limit of 1 minus p to the n plus 1 power. Now remember, p was a probability. Now, as a probability, the most it can be is 1, right? And the least it can be is 0, or something in between. So if it is exactly 1, the probability of success, well, this term cancels, and it's 1 minus 1 to the n plus 1 power, which is 0. If it is exactly 0, right, it's 1 minus 1, which is 0, to the n plus 1 power. So the 1 minus 1 cancels, you get 0. If p is between 0 and 1, well, you get a fraction, right? And if you multiply a fraction by itself, n plus 1 many times, as n goes to infinity, that term goes to 0. So you're left with 1 in either case. Okay? All right. Any questions about this? Does that make sense? Okay. So here we have this result. The infinite sum for x goes from 1 to infinity of 1 minus p to the x minus 1 times p is equal to 1. And therefore we've proven that, yes, this expression is a probability because it obeys the law of total probability. Okay? And so the tool that we use to do this is a geometric series. And we started out with the geometric series, and we showed through a set of manipulations what the closed form solution is, and then we substitute that closed form solution to our expression for the sum of probabilities and get our result. Okay? So please try this yourself and convince yourself that it really does work. And one of the things that happens when you're trying to demonstrate the development of a probability is you have to show that it behaves like a probability. And some of that it means, or in all cases, it means showing that the law of total probability is respected by this particular thing you think is a probability. Okay, so I'll end with this, and we'll pick back up on, I guess because we have a test Tuesday, next week, Thursday, with the development. And this is from the book. And now that we know that this geometric distribution is a probability, we show that the law of total probability holds true, that the sum of all the probabilities over all the values that x can take on equals 1. Now we want to compute the summary statistics, namely the mean and the variance. And so the result is, okay, if the probability of success for a single outcome for an interview is equal to p, p of x, and this is our probability, 1 minus p quantity to the x minus 1 power times p. For x goes 1, 2, 3, and so forth, right? Again, x means what we're calling k. The xth person is the one who gets higher. So what this probability traffics in is the position in line for the candidate, for the line of candidates that ends up getting higher. And so the first result, we talked about law of total probability, and that's been proven, and we make use of the geometric series, and the geometric distribution is called the geometric distribution because it derives from the geometric series, okay? And so the next thing with enterprise to do is to show that the mean of the geometric distribution is 1 over p. Now, in the book, this is the actual proof that we have up here. And what I'll do is start the unpacking of this, and we'll pick back up with the unpacking of the derivation of the mean and the variance on Thursday. But in the interest of time, let's see, we have 7 more minutes. So I'll just introduce it. So we have our infinite series. And that infinite series they're calling S of Q. All right? It's a series governed by Q. And in this particular case, Q is that constant factor we were calling R. So if we have S of Q is equal to the sum 0 to infinity Q to the x. So this means the following. S of Q is equal to the infinite sum x goes from 0 to infinity of Q to the x power, right? That's just equal to, well, for x equals 0, that would be Q to the 0 power, so that's 1. For x equals 1, that would be Q to the 1 power, that would be Q. And then we have x equals 2, that's Q to the 2 power, Q squared, and so forth. So S of Q, in this case, is 1 plus Q squared plus Q cubed, etc., right? Now, we said the general form for an infinite sequence, you can have a scalar a. So in this case, a is equal to 1. So I have 1 times 1 is 1, 1 times q is q, and so forth, right? So that is absolutely a geometric series. And when they have this expression, they say the geometric series form is as follows, right? Now you notice here, they excluded the x equals 0 to infinity. It's by context that you have to assume that the variable for this summation is going to be x. And they said the geometric series is equal to 1 minus q to the minus 1 power, right? So when we said 1 over 1 minus r, well, that's the same as 1 minus r to the minus 1 power. That's 1 over 1 minus r, right? If a is equal to 1 for the geometric series. That's the closed form expression. So in this case, they're using q instead of r, so they write that 1 minus q to the minus 1 power, okay? So here, they're just stating what the closed form solution is for the geometric series. In this first box here, they're showing you what the geometric series is in its general form, assuming a equals 1, and they're showing you here what the closed form solution is for that geometric series, okay? Now, in the second step, you notice here in the center, and you know, the book can be a little bit terse. It'll say SQ prime is equal to, and it'll have the expansion of what the series looks like, and it'll have prime. So that's the first derivative. So if we look at our sequence here, it says S of Q, right, is equal to that sum, x goes from 0 to infinity, of Q to the x power. Now, the derivative has the property that the derivative of the sum of things is equal to the sum of the derivatives. And what that means is, suppose if I said I had an expression x squared plus x cubed. If I wanted to take the derivative, d dx, of that expression, that's the derivative of the sum of terms. That's the same as saying d dx of x squared, the first term, plus the derivative d dx of the second term, right? So that's called linearity. So the derivative of the sum is the same as the sum of the derivative, right? And in this case, it would be 2x plus 3x squared, right? So if I were to take the derivative with respect to x of both sides of equality here, I take the derivative of s of q, right? And it's the derivative with respect to q, right? So if I took d dq, and it doesn't matter what the derivative is with respect to, it's just the variable and a function, d dq of s of q, s is a function of q, and I'd write d dq of that summation. X goes from 0 to infinity, q to the x power. So how do I write derivative of s of q? I write s prime of q, right? And d dq of that sum is the same, let me draw an arrow here, as the sum of the derivative of the individual terms. So I write from 0 to infinity, and I write d dq of q to the x power, okay? And so if I take the derivative of something raised to a power, I just say that power times the variable, and that power decrements by 1. So it's x times q to the minus 1 power, okay? So I put it all together, and I get this expression that s prime of q is equal to x times q to the x minus 1 power under that summation, okay? And so while the steps here are a little bit too terse or compact for my liking, what they're doing here is developing some expressions that you use that will end in the expectation showing that it's 1 over p, right? And so to prove that the expectation of a geometric is 1 over p, you need the first derivative of the sequence, and then to show the variance, you need the second derivative. And we'll pick back up a week from today and actually do all those steps, because I think it's important for you to get comfortable seeing some of this stuff instead of the very compact treatment that they give it in the book, which I think is unfortunate. Okay. Any questions about this? Okay, so that's about time. I don't think I want to introduce anything else. It's 1:14. So I will see you on Tuesday. Good luck on the exam.